15 minutes, you'll discover just how a helicopter flies. We'll take an interactive exploration into the basics of helicopter flight. We'll cover the 4 forces of flight. Then we'll show how the airfoil works, and finally go over the flight controls and what they do. For the purpose of this example, we'll place the helicopter in straight and level flight. Every aircraft has 4 different forces acting on it at all times: weight, lift, thrust, and drag. These forces act in pairs and are always in direct opposition to each other. It is these forces that we must manipulate in order for an aircraft to fly. The way we generate lift is through an airfoil. Airplanes have wings. Helicopters have rotary wings called rotor blades. If the speed of the airfoil increases while moving through the air, the lift also increases. Lift can also be increased by changing the angle of the airfoil relative to the direction of movement. This is called the angle of attack. However, as the angle of attack increases, the amount of drag also increases, making it harder for the airfoil to move through the air. There are a number of principles actually involved in producing lift. We are greatly simplifying what actually happens and won't be going into aerodynamic theory here today. However, it is important to understand that the airfoil produces lift, and the amount of lift varies with speed and angle of attack. Let's move on. With traditional fixed-wing aircraft, the faster it moves through the air, the more lift it produces. But a helicopter can fly without any forward movement at all. It can hover. Rather than moving the whole aircraft through the air to generate lift, helicopters use rotary wings. It is this ability to separate the aircraft movement from the generation of lift that allows a helicopter the advantages of vertical takeoff and landing. Helicopters don't need runways, and forward movement isn't required for the helicopter to maintain maneuverability. As the rotor blades spin, they create an aerodynamic force, which is a combination of lift and thrust. We'll call this total rotor thrust. An important thing to remember is that the total rotor thrust is always perpendicular to the tip path plane of the blades. In this animation, you can see that total rotor thrust is not always 90 degrees relative to the helicopter, but 90 degrees relative to the path of the tips of the rotor blades. The ability to vary the magnitude and direction of the total rotor thrust is what allows us to control the helicopter. Before we go on to how a helicopter hovers and moves through the air, there is something else we must first cover. To accelerate the rotor RPM is increased by turning the throttle located on the collective stick. A helicopter is designed to fly with the speed of the blades, the rotor RPM constant with little variation. So we turn the throttle to increase the power, which in turn increases the RPM of the blades. However, when we bring in power, there is a law, one of Newton's 3 laws of motion that will affect a helicopter. Do you know what that law is? According to Newton's 3rd law, the blades are trying to turn the helicopter in the opposite direction that they are turning. This is called torque. While on the ground, this problem is minimized because of the friction of the landing skids. So while on the ground, the body won't turn around the blades unless lots of power is quickly transferred to the rotor system, or the helicopter is on ice or floating on water. In most conventional helicopters, a tail rotor is used to compensate for the torque applied to the main rotor. The tail rotor is installed on a long lever, the tail section, and provides sideward thrust, which resists the turning of the helicopter. To control the tail rotor, we use the anti-torque pedals. These pedals change the amount of thrust generated by the tail rotor by increasing or decreasing the pitch, causing the tail of the helicopter to rotate right or left. Whenever the tail moves, the nose will turn in the opposite direction. Using the anti-torque pedals, the heading of the helicopter can be controlled. Stepping on the right pedal rotates the nose to the right. Stepping on the left pedal turns the helicopter to the left. Okay, back to hovering and moving through the air. Controlling the magnitude of total rotor thrust is accomplished with the collective pitch control. This control is the same one that has the throttle mounted on it. By lifting up the collective, we increase the blade's angle of attack, causing a greater total rotor thrust. Remember we said earlier, the helicopter's rotor blades are designed to spin at a fairly constant speed. When the collective is pulled up, what else must be done to maintain the proper RPM of the blades? When total rotor thrust is increased by lifting the collective, more power is required to maintain a constant RPM, which in turn requires an increase in throttle. As the total rotor thrust increases, we increase lift until it is greater than the weight of the helicopter and it starts moving up. The opposite is also true. If total rotor thrust is decreased by lowering the collective, less power is required and the throttle must be decreased. The throttle must be coordinated with the changes in collective. In some helicopters, the collective and throttle are mechanically correlated and only require fine-tuning by the pilot. All turbine and some piston helicopters have governors that precisely control the engine RPM. Now is when the cyclic control comes into play. When moving the cyclic control, the total rotor thrust will also move. For example, pushing the cyclic slightly forward causes the total rotor thrust to tilt forward. This will reduce the lift component and create a thrust component. Since the helicopter now has thrust, it will begin to move forward. It will continue to accelerate until the air resistance causes enough drag to equal the thrust, and then will stay at that speed. By tilting the total rotor thrust in any direction, we can move in any direction. But keep in mind that the directional thrust associated with the moving of the cyclic causes the lift component to be reduced. Raising the collective and adding throttle would increase the total rotor thrust and maintain or even increase altitude and speed. To get the helicopter back on the ground, we need to move the cyclic back enough to slow down and stop. Then lower the collective and reduce the throttle to settle onto the ground. The ability of a helicopter to land in limited spaces also gives it a unique safety benefit. The blades must continue to rotate. This is called autorotation. In the case of engine failure, a freewheeling unit allows the blades to continue spinning even though the engine is no longer providing power. A pilot in this situation is able to adjust the controls in such a way that the blades continue to rotate and the helicopter can glide back to the ground and land safely with minimum forward speed. The auto-rotation maneuver is an essential part of pilot training, and pilots continue to practice this emergency flight procedure regularly. Now, let's go fly. An important thing to watch is how the pilot controls the helicopter. You'll notice that the controls are moved very smoothly and gently. Just like driving a car, a helicopter is very responsive, so abrupt control movements are not required and should be avoided. And there you have it. That's how a helicopter flies.